we definitely are. Oh, it shows up here in the monitor. As this recording started. Now, as I've made clear from the beginning of the semester, I'm not enforcing due dates because we all have enough stress as it is. But unfortunately, at some point, y'all just run out of semester to work with. Okay, so this final grades for semester are due on Monday, December 11th. So I was setting the due date by which I must receive whatever you get. The last day of finals, December 7th. So please keep that in mind. I understand and accept, as based on previous semesters, that this means I will have a good amount of grading to do at the very end, but this is why I'm very efficient at grading for survival. Okay. Well, I also want to point out that this is implemented in the Canvas gradebook. So homeworks and quizzes are lumped together into one category, and that one category counts for 30%. But the lowest two assignments in either category, homeworks or quizzes, will be dropped. So that could be used to take a little pressure off toward the end. Okay. All right. Now, before I jump to today's material, still it's the same topic, numerical differentiation. I want to bring back something from last time. Right. This is an example that I presented last time, a 5-point formula for approximating the first derivative that uses values of f at x naught and then plus or minus h and plus or minus 2h, where h is the spacing. And so to get the coefficients of that finite difference formula, we set up and solve this system of equations. And oh, then we have here the okay, we have a formula for the arrow chart. Now, I have something strange in my MATLAB diary here. I'm not sure what to make of it. Okay. But anyway, look, what I'll do is show this how you can do this in MATLAB.
Another diary.
Okay. So that involves creating this matrix that has integers -2 to 2. Each column raised to the powers 0, 1, 2, 3, 4, where each row corresponds to a different exponent. So to create that matrix A, what I can do is, well, the first row is going to be all ones because everything is raised to the 0 power. So my first row will just be a row vector of ones. Wait, let me put a comment as what I'm doing here.
Yeah, what?
So A will be first a row of 5 ones. So here we're using a ones function with one row, 5 columns. This is a row vector of all ones, 5 rows. That's the first row, so I mark that the end of a row by a semicolon. And then the next row is minus 2 to 2 raised to a first power, so that's just going to be minus 2 to 2. So I can use the colon operator for that, minus 2 to 2. Because the colon operator produces a row vector of numbers. Okay. And then the rows that follow are minus 2 to 2 raised to the second, third, and fourth power. So for that, I use a dot. So I have minus 2 to 2, and I want to square it, but if I do this to square it, that's going to be an error. The up arrow operator for exponentiation by itself is only used for square matrices, for scalars. So I use a dot up arrow for exponentiation of a vector. And then third power and that row to fourth power. Okay. So now I have my matrix. Okay. And then the right-hand side of the system, the vector of all zeros, except for 1 in the second position. So I'll go ahead and create that column vector. And now I can solve for the system for coefficients. So C is equal to A backslash B. So that's how you solve system linear equations in MATLAB. It's a matrix, backslash, and then the right-hand side. So this is equivalent to
A inverse?
yes. Okay, but you would not want to actually. You could have MATLAB explicitly compute A inverse and then multiply it by B, but that takes about 4 times as many floating point operations, so it's not advised. Okay, so now we have the coefficients, but I didn't display these as fractions, so I use
That's your meeting.
is that my meeting?
Yeah. You can never see the board.
That's really strange because it's been recording for 8 minutes.
Well, I just joined.
Oh, gotcha. Oh, sorry. Go ahead and send class twice.
Oh, yeah.
Okay, so if I do format rat,
Format rat.
and display C again. Okay, so now we see it as fractions. So to compare with what I have in the notes from last time, so this is the first entry is for the coefficient of x naught minus 2h, then x naught minus h, then x naught is 0, so it won't appear. X naught plus h, and then x naught plus 2h. And that is consistent with what you see here. So 1/12 for extremes, and then plus or minus 8/12 for 2/3. Okay. Now, I can also show you what's going on with the error term, because here's the formula, the general formula for the error term. So I have a total of, I have n equals j plus k. J and k are both equal to 2 in this example. So my error is going to be minus h to the fourth over 5 factorial, which is 120. And then I have this expression right here, which is multiplying all the coefficients by my indices raised to the next power, which is going to be 5. So if I go ahead and compute that, factor in my error term is going to be minus 2 to 2 raised to the 5th power. Now that is a row vector, and if I multiply that by my coefficients, c, that c is a column vector. When you have a row vector times a column vector, that is a dot product. That's what I want. I want to multiply corresponding elements of these vectors and add them all up. That will give me this summation right here. And what I get when I do that in this case is minus 4. Okay. So with this summation being equal to minus 4, so now I have minus 4 over minus 120 is
It's not, this thing's not giving me, this thing's not giving me 4, it's giving me an error.
okay. I will post the diary, and you can look at it to see where things went wrong.
Where am I getting wrong? Invalid expression.
It must have been a typo earlier. So you have h to the 4 times minus 4 over minus 120 is plus h to the 4 over 30. And sure enough, that's what we have, the coefficient of the error times the 5th derivative, remember n is equal to 4, at an unknown point. Was this a command that you typed?
Keep doing the comma instead of the colon.
Okay. That would do it. Okay, any
Yeah.
questions about this example right here? Last time I also had an example about higher order derivatives. Okay. Right. So if I set up this system of equations, second derivative formula. Right, well, really this would be minus 1 to 1 raised to the 0 power, minus 1 to 1, raised to the first power, minus 1 to 1, raised to the second power, and that's the matrix. And then my right-hand side would be a vector of all zeros except for a 2 in the third position. That's what you always use for second derivative. It's the order of derivative factorial in whatever the order is plus 1 is the position that it goes in. So then I solve that system of equations, and sure enough I get coefficients 1, minus 2, and 1 that you see in this approximation here.
I don't type very fast.
Okay.
I don't type very fast.
I've been wondering if it's possible, because here I'm raising it to whatever power appropriate to each row. If I could have one expression that would generate a whole matrix, but I don't think that might not be possible. I I can try something really. See. Okay.
Forward slash.
So I want to raise -1 to 1 to the powers 0 to 2. Okay.
A equal. Wait,
So let's see what happens.
wait. Colon.
Oh,
colon.
that's very much not what I wanted. Oh, got it. Okay. This I still can't explain.
What did,
But yeah, if I take my indices, dot exponent, if I take the
what was that now?
and I take the exponents I want and I put a transpose there with a single quote or apostrophe, make the exponents a column vector. So row vector of indices exponentiated to column vector of exponents seems to do the trick. Okay, all right. So this comment was at least correct, but I expected to get an error or something. Now, if I go back to the previous example, with a 5-point difference rule, so I do -2 to 2 raised to the exponent 0 to 4 transpose, and let's make sure about this. Yeah, that's the matrix. Well, I'll be dang. All right. Okay. So this is one approach. The approach I covered last time is for generating coefficients of finite difference formulas for approximating derivatives. But the focus of today is an alternative approach to generating such formulas. Diary off. Okay. That is using Lagrange polynomials. So the idea is this. The function we want the derivative of, we're approximating it by its Lagrange interpolating polynomial. So presumably we could approximate f prime at x naught by taking the derivative of the interpolating polynomial and evaluating that derivative at x naught. So the thing is, I've been describing a approximate derivative as a linear combination of values of f that select points. So the coefficients of linear combination would be the derivatives of the Lagrange polynomials at the point that you want, at x naught. So we can get the coefficients that way instead of using Taylor expansion. Okay. Now, that's essentially the approach. That you're differentiating Lagrange polynomials to get the coefficients that you need. Now, the way that you can get Lagrange polynomials, of course, you have a homework problem on this. Make Lagrange, although I had to use a different approach in the homework problem, but what you can certainly do is use MATLAB's polyfit, where the x values are the points that you're plugging into f, and the y values are equal to all zeros except one of them is equal to 1, because that's how Lagrange polynomials behave. And then once you have the Lagrange polynomials that you want, you can use polyder to take the derivative of Lagrange polynomial, and then you plug in x naught using polyval. So all these MATLAB polynomial functions can be used to to get the coefficients. So polyfit to make a Lagrange polynomial, polydir to differentiate them, polyval to evaluate at x naught. Now, this approach, and really the Taylor series approach as well, or Taylor expansion approach, none of those actually require that the points involved be equally spaced. That's a convenience. Now, but when you do have equally spaced points, you can make things a little simpler. So let's suppose, just like last time, that these are both x values equally spaced, indexed from minus j to k. So these define our x values at which we're evaluating f. Here's what we can do. Instead of interpolating at the x values themselves, we can interpolate at the indices, minus j to k. So interpolating at these points and evaluating at x naught is equivalent to interpolating at the indices, so these integers, and evaluating the derivative of Lagrange polynomials at 0. And then whatever coefficients you get, those will be constants, and you divide it by h, and there's your differentiation rule. Now, the reasoning behind this, the reason why this works, is what we're performing is a change of variable. So this change of variable, u, is defined to be x minus x naught divided by h. So what this does is it maps the original x values that you're plugging into f to the integers minus j to k, in the case where these points are equally spaced. So here's an example of that. So I want this differentiation, a finite difference formula using these points. This is an example that was worked through last time, the Taylor expansion approach. So if you consider the spacings, x naught plus h, x naught plus 2h, my multiples of h are 0, 1, and 2. So actually, I'm going to call these interpolation points u equals 0, 1, 2 because we're changing to that space. All right, I should have used u here. What I'm going to change it. And that's why I displayed the notes in this particular program, that I can edit them as I go and make improvements from one instance of the class to the next. Even though this will take a little bit of time. You get to tell me if I missed it. So x naught corresponds to u equals 0. So this is a Lagrange polynomial that's equal to 1 when u equals 0, but it's equal to 0 when u is equal to 1 or 2. So then I take its Lagrange polynomial, I take its derivative, and then I evaluate it at u equals 0, and I get minus 3/2. And then I do the same with the other two Lagrange polynomials. So these three Lagrange polynomials are for points 0, 1, and 2. So this is equal to 1 at u equals 1, and it's equal to 0 when u is equal to 0 or 2. Take a derivative, plug in 0. So I do that with all three Lagrange polynomials, and I get the coefficients of my finite difference formula. So I take these coefficients and I pair them with their associated f values. And then here I've just cleaned up a fraction a little bit. So this is the finite difference formula that was derived last time using Taylor expansion. The formulas are equivalent. So Taylor expansion and Lagrange interpolation produce the same finite difference formulas because Taylor expansion too, you're approximating f by a polynomial, because you're cutting off a Taylor expansion at some point. So, so any questions about the Lagrange approach? Um, Alright, so more generally, f prime is equal to the summation of these coefficients times the corresponding f values plus some error. And these are the coefficients. But actually, okay, I'm gonna specialize this to the to case of equally spaced points. Because this formula does not require that the xi be equally spaced. Here's use a conventional 1/h factor out front. Where each coefficient is the derivative of different Lagrange polynomials. So here I use tilde. And these Lagrange, so these Lagrange polynomials are different from these, that indicated by the tilde on top. Okay. Interpolate at the integers. These coefficients, the c's, are not exactly the same because they differ by a factor of h. So I'll indicate that here. And for completeness, okay, so these Lagrange polynomials are functions of x. Interpolate at the x values for the equally spaced case. These Lagrange polynomials with the tildes interpolate at the indices. Okay. As far as the error formula is concerned, we use the formula for error in polynomial interpolation. So, because the error formula for polynomial interpolation is for f of x minus pn of x. So, what I'm literally saying is that the error in the derivative is the derivative of the error. So I have f prime of x naught minus my interpolating polynomial prime of x naught. So that's going to be the derivative of this. This is a polynomial interpolation error, theorem 7.4.1, evaluated at x equal to x naught. And what ends up happening is when you take the derivative of this, okay, you're using the product rule. But almost all of the terms from a product rule will become 0 once you plug in x equal to x naught, because x minus x naught is one of these factors in this product. So the only term that arises from a product rule that isn't going to go away is the one that differentiates the term x minus x naught, which would be 1. So in other words, it's all of the terms in this error formula except for x minus x naught. And then you plug in x equals x naught to be all the other terms. So now we have this. Okay. Now this is consistent with what happens when you this error formula right here, again, does not assume that the points are equally spaced. Okay. Now, in the case of when they are equally spaced, this error formula does simplify. I've made that the subject of a homework problem. Hashtag sorry, not sorry. Okay. Generally speaking, the order of accuracy is h to the k plus j. But as I mentioned, sometimes it could be a higher order accurate in cases of symmetry. Now, okay, so are there any questions about what I've shown you here? The same approach for Lagrange polynomials can be used for higher order derivatives. So all you're doing is, if you want second derivative, for instance, you just take the second derivative of Lagrange polynomials. So you're doing something like this. Although in those cases, unlike Taylor expansion, the error formula is harder to come by. But I won't get into that here. It's a mess. Because you have to take derivatives of this, and it involves a derivative of finite difference, and it's yikes. Okay. All right, last thing we'll discuss with regard to numerical differentiation is sensitivity. Now, this is going back to a topic from chapter 2, where we have forward error, backward error, and then how they're related by the condition number. So we recall that's the definition of a condition number. So, okay. So in this context of computing approximate derivatives, the forward error is the error term that you get from your finite difference approximation. So as an example, here we have what's referred to as the forward difference. Actually, I should, you know what? This is something I should have mentioned last time. Okay. I mean, in class, I focused on how you carry out these approximations, how they derive these approximations using Taylor Lagrange. But I've shown you a few specific ones, but the most commonly used ones are right here. Okay. And this one you would recognize, basically it's a definition of derivative, but taking away the limit part. And that's called a forward difference. This is the error. And I actually think this came up in a homework problem, an exploration from chapter 2. Because the error has h raised to the first power, so we say it's first order accurate. So it's the error is big O h. So it's not great, but it's very simple. Similarly, we have, if I've ever replaced h with minus h throughout this, I get what's called a backward difference formula. So again, very similar to the definition of derivative, also first order accurate. And then if I take the average of these two, then the terms involving f of x naught will cancel, and the errors, the leading terms of the error, will also cancel. And we have this. Now, this actually, I believe, this is the subject of an example from chapter 2. That's called the centered difference formula. This one's probably the most commonly used because it's just as simple to evaluate as these two, but okay, so here I'm like repeating, like chapter 2, the derivation of the error term, and it turns out to be big O of h squared. So those are the three most commonly used finite difference formulas that use the value of f at only 2 points, but they're low order accurate, as opposed to the what I showed you last time, a 5-point formula that is 4th order accurate. The error is order big O of h to the 4th. Oh yeah, this is a function I made up to show how computing derivatives using differentiation rules, like some software does, can get extremely ugly. The derivative most fun to compute. As an example, suppose we want a derivative of this function at x equals 0.25. So if I go ahead and go trouble computing this and evaluate this formula at x equals 0.25, then I get this result here. That's like the exact value, so many decimal places. But if I use the center difference, I use h equal 0.005. So I'm taking this expression. Now this is not so nice either, but it's way nicer than this, certainly. And evaluate that at these 2 points. Then I get this result, and that's accurate to a few decimal places. And I could have chosen a smaller value of h and done even better. So this shows how there's a lot. So yes, you're sacrificing some accuracy, but not a whole lot of accuracy, and you're gaining a whole lot of efficiency by using these finite difference formulas instead of having your software carry out symbolic differentiation like this. This function like this would be very difficult to represent internally, very cumbersome at least. Question about what happened here. All right. So, okay. So in this case, this is the forward difference. So that's the error term that I showed you a little while ago. So in this context, this term right here, minus h over 2 f double prime and squiggly, that's the forward error. Because forward error is the error in what it is you're trying to compute, in this case, the derivative. Now, what about backward error? So we assume that the compute solution is the exact solution of a nearby problem. Well, that actually is very much true for numerical differentiation. So whatever approximation we're computing using a finite difference formula of f prime of x naught is the exact solution of a different differentiation problem, that of computing a derivative of a interpolated polynomial, Pn of x. So remember, backward error is the difference in inputs rather than the difference in outputs. So if you remember the backward error related problems from, this would have been from homework 2. So you have your exact value y, your exact output, and then you have your approximate output y hat. Then you have your true input x, and then you have your approximate input x hat. And the exact solution to that problem is your approximation. So if we think of this is y, f prime of x naught, this is y hat, the approximate output. So then the true input is the function you're differentiating, f of x. Pn of x is the approximate input. So, so the backward error is the difference between your true input, f of x, and your approximate input, which is Pn of x, which is the polynomial interpolation error. So that's what backward error means in this case. So this is why we studied all that stuff in chapter 2. Now it's relevant. Okay. So an example of forward difference, all we're doing here is we're approximating f of x by a linear function. So a first degree polynomial that interpolates f at x naught and x naught plus h. So doing something that was seen in an example and also in homework 5, linear interpolation error, so that'd be f double prime unknown point over 2, and then we have these linear factors multiplied here. And actually, this just came up an example from section 7.4. This has its absolute maximum at h squared over 4. So then I get h squared times the maximum of second derivative divided by 8. So this right here is a bound on my backward error. So what's my condition number? The condition number, absolute value of forward error divided by backward error. Notice both the forward error and the backward error cancel the second derivative. So you can say they cancel. That's a bit non-rigorous, but we're just trying to get an idea of what the condition number behaves like. So what we have is h over 2 divided by h squared over 8. So when you simplify all that, you get the condition number 4 over h. Why is that not good? What? I'm sorry, I totally cannot hear you.
If you have a denominator of 0.
Yeah, because h is meant to be small.
Yeah, so it's converging to 0.
Yeah. So h is converging to 0. So for small h, which is what you normally use these fine difference formulas, the problem of numerical differentiation is ill-conditioned. And this doesn't even take into account that what happens with rounding error, because when h gets smaller and smaller, these values get close together, you are risking catastrophic cancellation. And actually, I did demonstrate that way back when we were in chapter 2. Now, what we'll find though is that when we, the next time when I start, so on Tuesday when I start numerical integration, we're actually going to find that, I guess I'm spoiling my own lecture here, but numerical integration, and I'll show you details later, is well conditioned. And the thing is, of course, integration and differentiation are inverse processes. So if you have a problem that is ill-conditioned, then going the other way, so where the roles of input and output are reversed, that has the effect of flipping the condition number, which makes sense because condition number is forward error, error in output divided by error in input. If the roles of input and output are reversed, then that's going to lead to reciprocal of the condition number. And that concludes numerical differentiation. I'll be spending a whole lot more time on numerical integration because that's much more interesting anyway. Okay. There's time for questions on anything, such as homework or. It's not well done for because it's after 6 p.m. Okay. I've been here for a long time. Okay. Right, so we're back in it.